So week 10, problem 10.42, in which we have a steam power plant operating on ideal Rankine cycle with regeneration. So we have a regenerative Rankine cycle. First word that's important, ideal. What is that saying? That we have, we don't have any irreversibilities, right? So this cycle, the isentropic processes are indeed isentropic. There's no change in entropy. We're not generating any entropy when we're compressing or when we're expanding. The next one is this guy here. So whenever we have regeneration, we're going to have a different setup. It's a different system in which we're going to use part of the energy that would otherwise be discarded or otherwise would be rejected. We're going to actually use and plug it back into the system. Okay. We have steam entering the high pressure at 6 megapascals and 450. So that's going to be our high end. And it's condensed to the condenser to a pressure of 20 kilopascals. That's our low end. The steam is extracted from the turbine at 0.4 megapascals to heat the feed water in an open feed water heater. So this is the new thing. So this has to do with this regeneration here. Okay, so the regeneration is precisely this open feed water heater that we're going to use to get back some of that energy that we otherwise discard. Water leaves the feed water heater as a saturated liquid. Okay, so I'm going to draw this on the diagram for us to have a clear picture of what's going on, and from that point on we can try to make sense of this information that's being given to us. Okay, we need to show the process on the TS diagram with respect to saturation lines, and we also need to calculate the thermal net power output and the thermal efficiency. Okay, so let's quickly draw what is happening here. So we're going to have temperature on this end, entropy on this end here. And if you guys recall, remember when I did the little energy diagrams? So let me just do this on the bottom here. Remember we had state 1, and then we had a little boost in energy from state 2. That's when we compress it. And we went all the way up to state 3. That's where we have the boiler giving a lot of energy. And then from state 3 to state 4, that's when we get the turbine doing the work. And then we have to go all the way down back to state 1. Right? That's a bit of the energy layout that we have on this. Now, on this case here, what happens is, like I've actually talked about this before, right? Instead of just rejecting all this energy that we would need to reject to go from 4 to 1, we take part of that energy and we plug it back into our system. Instead of rejecting everything, we get some of that back. So the idea is that when we do that, instead of placing everything away, we can use this open feed water heater to get some of that back. Let me grab one of the drawings that I have here to do it. So let's think about it that way. Remember the way this worked is we had a boiler here. We had a condenser here on the bottom. And then we had the pump or the compressor and the turbine. Okay, so we would go from, we had saturated liquid here, put that through the pump. We have compressed liquid here, put that through the boiler. We'd have vapor here, hopefully superheated. Put that through the turbine. We'd have a mixture here. Then we put that through the condenser, so we would have liquid water again. But then, if I want to include an open feed water heater in this guy, what I need to do is I'm going to take this pump away, put it on this corner here, this guy like this, and then what I'm going to do is once I hit my turbine, instead of making everything leave and go into the condenser, what I'm going to do is I'm going to have the open feed water heater, and let's do it like that, open feed water heater over here, and then part of my steam is going to go like before to my condenser, but also part of it is going to go through our open feed water heater. Okay, so that means that we can actually save some of that energy, and we can mix all that up again. And then we're going to have need a second pump over here so that we can have this compressed. Okay, so how will this, close our boxes here. Okay, so how will this work? Well, like before, we're going to start down here on a state of saturated liquid. We're going to put that through the pump. Then we're going to go into the mixer. So this mixer is going to have a mid-range pressure. Okay. This mixer is where I'm calling it a mixer because it's a chamber in which the liquid that's being pumped is also being mixed with the water coming from the open feed water heater. So we're going to have a mid state here, right? And that mid state is precisely this idea here of grabbing some of the energy back and forth. Then, once we have that mixed up, we're going to put that through another pump. And this other pump is going to ensure that before the boiler, we're putting a high compressed liquid through the boiler. We're going to put it through the boiler. We're going to have vapor here again, like before. Then we're going to put this through a turbine. And then when it leaves the turbine, we're going to get some of that mass flow rate of water and place it through the open feed water heater so that we can save some of that energy. And then we're going to have another part that's going to come out here. Get rid of this. Then a part is going to come out here and go through a second turbine. Okay, so that's kind of the setup of what's happening in this system here. Okay, so the most important thing is to understand that now the turbine, it has two outputs. One that's going that way and one's going this way. I'll draw this on the TS diagram, and this is probably going to make more sense to you guys once I do that. So let's go up to my TS diagram over here. Okay, and then we start down here on 1, just like before, and we're going to go straight up on an isentropic process all the way to 2. Then we're going to come on the isobaric. We're going to stop here in the isobaric, have a second pump that's going to pump here. Isobaric again, all the way until we have, hopefully, our superheated state. From our superheated state, we're going to drop. And then we're going to drop all the way down, but we're going to have a mid stage right there, right? So we have mid state here. So we're going to have one in here as well. So what does that make for us in terms of state? 1 state, 2 states, 3 states, 4 states, 5, 6, 7. Okay, so let's see what's happening here according to what we just talked about. We have, let me put some arrows too so that we know where these guys, I'm sure that you guys know where this is going, but just to be extra sure. Okay, so we have our saturated liquid. We're going to compress it into a pump, and then we're going to put it into the feed water in the mixer there, right? That's where the mix is happening. Okay, this mixer is receiving both from state 2 and from state 6, but let's leave 6 for now. Then we get that mixed state and we pump it up again so that we're sure that we have a high compressed fluid going into our boiler. This is our boiler here. Goes through our boiler all the way until we have vapor. And then we go through the turbine. So this is our first turbine here. This is turbine number 1 from 5 to 6. And we're going to extract some work out of this. And then we go on 6, we're going to split, right? Part of the water is going to come through here so that we can put it through the open feed water heater and make use of some of that energy back to our system. And part of the energy is going to go down here to 7, in which we're going to have a second turbine. So we're going to have another work being outputted here, work 2. Okay, then whatever is left at the end of the second turbine is going to have to go through the condenser so that we ensure that what's coming back to 1 is only liquid. In terms of TS diagram, I don't think it's that big of a deal. I think it's easier for you guys to understand. Only thing that we're missing on this drawing is our dome. We can put that here. Let's do green. Okay, we know this guy here has to be right on the line because it's saturated liquid. The problem is also saying, if you guys recall, that steam is extracted from the turbine at 0.4 megapascals, and water leaves the feed water heater as a saturated liquid. Okay, so this is a feed water heater, and then it's leaving and it's reaching 3. So 3 has also to be a saturated liquid. So our dome goes like that, and then hopefully this number 5 is going to be outside the dome because we're going to have superheated fluid, and then it should do something like this. I'm not sure about, I haven't done the calculations yet for this guy, so I'm not sure if it's superheated or not. I'm not sure if this guy is saturated vapor or if it's a mixture, I'm not sure. And I'm not sure about this guy either. So for now, the dome is just what we think will happen. But if we find out that this is not the situation, we're gonna have to come back and make it right. Okay, so So far, do you guys have any questions? Because this is one of the hardest parts, is actually understand what's happening here. And if you guys don't have any questions, we can move on to start solving this. Okay, how are we going to solve this? And guys, please do stop me if you have questions, all right? Let me just do one more thing here, okay? I'm just gonna put the isobaric lines here. So this is all same pressure right here. This is all same pressure right here. And then this would be all the same pressure right here. Okay, these are all the same pressure. All right, so what do we know information-wise? We know heaps of things already, right? We know the pressure, and we know pressure 5, which is the same as pressure 4. And they're the high end, that's a 6 megapascals. We also know the pressure 1 and pressure 7, which is also the same. And that is the low end, that's 20 kilopascals. Okay, and we know pressure of the feedwater heater, which is going to be the same for 3 and 6, and that's 0.4 megapascals or 400 kilopascals. We also know T5 before it goes to the turbine, that's 450. Okay, so just looking at the information that we have, we can anticipate some things. We can anticipate that 1 is defined because we know it's saturated liquid and we know the pressure. With 1, we can find 2. 3 is defined. With 3, we can find 4. 5 is defined because we have temperature and pressure for 5. So we can use that to find our entropy. And then if we have entropy, we have entropy for 6 and 7 because they're the same entropy. And with that, we pretty much define 6 and 7 as well because we have the pressure for 7 and we have the pressure for 6. Okay, so that's how we're going to solving. The solving of this is not very different from what we did before. It's just understanding what is happening here. Now, one last detail that is important before we start solving this cycle is the following. Okay? Because, and I don't think I have a proper color anymore. Because we're splitting up here on 6, we're splitting up the water. We're going to have a Y here and a Z over here. Y is the proportion of water that's going on this direction here, while Z is the proportion that's going on that direction there. Now, because we can't really create or destroy any mass, we know that whatever Z plus Y are, it's going to be 100% of the original mass of water, right? So we can rewrite Z or Z if we want to as 1 minus Y. So this guy can be, instead of Z here, I can actually have this as 1 minus Y. Okay, so in other words, I'm splitting up, and then Y is the portion that goes to the open feed water heater, and 1 minus Y is whatever goes through the second turbine. Okay. If you don't have any questions, if you do, speak up. If not, let's start solving this. Okay. Step 1 is we have 20 kilopascals, and we also know it's a saturated liquid. So that's straightforward. We can go to table E5 at 20 kilopascals, and you can grab enthalpy 1, specific volume 1, which we'll use to find the second one, right? So the first one is 251.42. And this guy is 0.00 1017. Okay, so this one's done, defined, finished. As easy as that. Now we can do the next one, state 2. And state 2, we know that the work of the compressor or the work of the pump is the difference between H2 and H1, which is also approximately specific volume 1 times the difference in pressure. Right, so like last week, we can define this guy to be 251.42 plus 0.001017. And then we're going from 20 kilopascals to 400. So it's 400 minus 20. Right? So we have this answer in kilojoules per kilogram. Note this is tiny, right? This multiplication here is tiny. So we would expect H2 to be very close to H1. And what I got is 251, yeah, indeed, 251.81. So it's just decimal increases from 1 to 2, because we're not doing that big boost in pressure like before, right? We're just going from 20 kilopascals up to 400 kilopascals. It's not that that big of a boost as will be on the next pump that we're going to go all the way up to 6 megapascals. Okay, so that's state 2. That's done. It's easy as that. Can move on to the next state. State 3, and state 3 is going to be exactly the same process as state 1 and 2. Because state 3 is also defined. It's a saturated liquid. And we know the pressure, that's 400 kilopascals. So table A5, we just look for H3, which will be the same as H sat liquid. I have 604.66. And I'm also going to grab this guy because I'm going to use this to find state 4. Okay, so it's literally the same process we just did. Unit 4. Okay, so with state 3, I can go ahead and do state 4. And I know, write it straight off. It's going to be so it's going to be H3 plus specific volume 3, and the difference in temperature. Now this time we're going from the 400 kilopascals, and we're going all the way up to the 6 megapascals. This is a bigger jump in the pressure scale. Make sure I have kilopascals to maintain my kilojoules per kilogram. And I got H4 to be 610.73. Okay, now you defined 1, 2, 3, and 4 just like that. 5 is also going to be very quick to define because 5 have everything we need, right, for 5. So state 5. We have the pressure and temperature, right? So state 5 has 6 megapascals, and it's also at 450 Celsius. Okay, so we're going to note that T5 is greater than T sat at 6 megapascals, or you can do the other way around. You look at the table and you can look at the pressure table as well. Oh, sorry, on the temperature table and find pressure. It's going to tell you this is a superheated fella. If it's superheated, that means we're going to be looking at table A6 instead of A5. And we just need to grab the information over there because we have both temperature and pressure. So we can grab H5 and also entropy 5, right? Because that's what I'm going to use to find state 6 and 7, since we know they're both isentropic expansions. So for 5, I got 302.9 kilojoules per kilograms, and the entropy 6.7, 219. And with that, I've defined state 5. So let's have a look at what we did so far. Let me just highlight this guy. Okay. So we have state 1, 2, 3, 4, and 5 completely defined. Okay. We're as easy as that. And now we can do 6 and 7, and it's going to be as fast as this as well, because 6 and 7 are defined. We have 2 properties for them. We have the pressure in both, and we have the entropy in both. The entropy, which is precisely 6.7, right? It doesn't change. Okay, so let's do states 6 and 7 so that we can start looking for whatever they're asking us to find. Okay. Let me zoom in again. For state 5, so let's do state 6. In state 6, we know two things. We know this guy is at 400 kilopascals, and we also know it's S6 equals S5. Okay, so what I'm going to do is let's do it together. Let's grab our property tables and have a look. Share F property table. All right, so at the water pressure table, okay, and I'm going to be looking at 400 kilopascals, which is our state 6, 400 kilopascals, and I want to look on the entropy column, right? So what are our entropy? So we have this guy on the saturated liquid, and this guy on the vapor. Our value is 6.7, right? So 6.7 falls between 1.7 and 6.8, so therefore it's a saturated liquid. Saturated mixture. But since we're here already, we can go ahead and look at the 7th state, because that's 20 kilopascals. 20 kilopascals. It's going to be this guy and this guy. And again, it's 6.7, right? Because it doesn't change. So state 7 is also a saturated mixture. Okay, so what we're going to do from this table, we're going to grab these two values for state 7. We're also going to grab the values for enthalpy, because we're going to, since it's a mixture, we're going to have to use the mix between them to find the proper enthalpy. On the 400 side, same thing, right? I'm going to have to grab these values here for enthalpy as well, and these entropies here to find the quality. So let's go ahead and do that. So from the table, we just found out that S liquid is smaller than our S6, which in turn is smaller than the S vapor. Therefore, it's a saturated mixture, which means that our quality can be found. Quality can be found by doing S6 minus S liquid over S vapor minus S liquid. You have everything we need. Just plug in and find that this is 96%. 96.61%. Okay, with the quality, we can calculate our enthalpy. As we know, enthalpy is going to be enthalpy of state 6 will just be the enthalpy of the vapor times the quality plus the enthalpy of the saturated liquid times 1 minus quality. Okay, so we have all that information from the top the table, and we have the quality already, so we can calculate H6, and that's 2665.7 kilojoules per kilogram. State 6 is done. We're going to do state 7. So we can do state 7 now, which is exactly the same idea, right? So state 7. We know this is 20 kilopascals. We know S7 is also equal to S5, so we have that guy. And we already looked in the table and we saw that the same thing applies, right? S liquid, S7, S vapor. And this happens at 20 pascals as well, 20 kilopascals as well. So therefore, this is also a saturated mixture. So therefore, we're going to do exactly the same thing. We're going to find our quality by relating S7 minus S liquid over S vapor minus S liquid. And this guy is 83.25%. Okay, so I can calculate my H7 like before. That will be vapor times X plus H liquid times 1 minus X. And I got, for this one, I got 2214. 22. Okay, so pretty much we defined the whole cycle. Let's zoom out and have a look at what we did. All right, so I have all the states here. So let's look one at a time. Zoom in a bit more. Okay, so I have H1 on top here, You have H2 over here, H3, H4, H5, H6, and H7. Okay, so I have all the H's defined. I have 2 properties for each state, so that means my life is easier. Okay, I can now find whatever they throw our way, we can find out, right? So, what do we do now? What are we being asked? Well, first thing you can do is have a look at our diagram to see if it checks, right? See if it makes sense. Okay, so I can see already that this does not make sense over here because my 6 is not saturated vapor, so I cannot have it over there. So I need to have this still happening, this is still happening. But my dome cannot be right there, right? My dome has to go around. So my dome is going to go something like this. Because we know these 2 guys here, 6 and 7 are both mixtures, right? So they cannot be on the dome and they cannot be outside the dome, it has to be inside the dome. Okay, so now our TS diagram is correct. Messy, but correct. Let me actually get rid of some of these guys so it's less messy. Okay. The other thing that we know now is that, well, that's all we know, I guess. For now, what we need to find out now is need to find out these y's, see how we can keep solving this, because we're looking for the net power output, and to do that, what we need to relate is what is going in and what's coming out, and we know that our Q in is coming on here on top, and we know our Q out is coming down here, right? That's our Q out there. Now the problem is that for the Q in, we have all of the mass flow rate of water going through, right? So when we're going from 4 to 5, all the mass of water is going from here to here. However, when we're going from 7 to 1, which the heat rejection takes place, we only have part of the water because we know part of it went this way and the remaining went this way. Right, so the remainder of the water is down there and part of it is there. So we need to find what y is to be able to know the work. Now, I'll show you this mathematically because it's going to make more sense, I guess. Okay, so we want A, and in A, we want the power, right, the net power output. And we can do that by relating the 2 turbines and subtracting the 2 compressors, 2 pumps, or we can go ahead and do Q in minus Q out. It's the same thing as it's in the cycle, right? The only problem is, if you notice, we're always dealing with kilojoules per kilogram, right? And in the case of this guy here, this is not the same mass that's dividing both of them. We can think of it this way. Let's think of it this way. What we have there on all of these, if all these guys are energy, we're calculating this over mass flow rate. However, this mass flow rate here, this guy here, this mass flow rate here is different than this guy here. So we need to find out what's the proportion of the total mass flow rate that Q out has so that we can plug the values in. Okay, so let's write this in another manner. So Q net will be Q in minus Q out. Q in is from 4 to 5, so that means that you can just get 5, subtract 4. I'll have my Q in. But for this guy, it's from 7 to 1. But I still need to know how much is going through there. What's the proportion of the total mass weight is going through there? So if it were not for this guy here, I could just solve this now. But I need to find y to be able to solve it. Finding y is something very, very cool that we can do using energy balance and mass balance. Okay, so let's think about our TS diagram for a second. We have 1, 2, then we go to 3, and then we go to 4, and we just want to look at this guy for the moment. Okay, so this is 3 right there. This is 2. We have 4 up here, and we have 6 over here. Okay, and let's have a look at this guy here, number 3. Let's do an energy balance and a mass balance on this guy. What do we have there? We have 0.3 there, and mass-wise, we have mass flow rate 3 going out of there, and a mass flow rate from 6 coming in and the mass flow rate from 2 coming in. Okay. Likewise, energy-wise, what we have there is exactly the same thing, right? If we do a little energy balance, let's do a little control volume here. What is coming into this control volume? Well, it's the mass flow rate from 6 and the mass flow rate from 2. And what is leaving this control volume? The mass flow rate from 3. Energy-wise, same thing. Energy is coming from 6 and 2 and leaving from 3. So we can do both energy volume and we can do mass balance and energy balance. So let's do first mass balance. So what does a mass balance tell us? Well, it tells us that mass of 3 has to be equal to the mass coming from 2 plus the mass coming from 6, right? If we want to put things in terms of y, what is y? Y is the proportion of how much is being split to this feedwater system. So y is just how much water is going to the feedwater system in respect to how much water we have in total. And what is z? Z being the other part, right? Z or 1 minus y, same thing. Z is just how much is coming from 2 over the whole thing. So our mass balance gives us these relationships here. And our energy balance, which is the next thing we're going to do. Our energy balance says that all the energy that's going into this control volume has to be equal to the energy that's leaving, right? So because we can't create or destroy energy, that means the energy going into is the same as the one leaving. So the energy going into 3, and we can do energy rate in this case here, right? Power leaving from state 3 has to be equal to the power coming from state 2 plus the power coming from state 6. Okay, and with these two balances, we can do a little magic math and just find what is the proportion. Note that we're not going to find the actual mass flow rates. We can't do that, right? But we can notice the proportion that's being transferred from one side to the other. So what I'm going to do is I'm going to divide everything by M3 first. So this is going to be H3 equals M2 over M3. M3. Okay, and you notice that this guy here is the same thing as 1 minus y. And this guy here is the same thing as y, right? We can actually check here. Yeah, so 6 over 3, that's the y. And 1 minus y, that's the 6 over 2. So this guy, this equation here can be rewritten as H3 equals 1 minus y times H2 plus y H6. And now we just had the only unknown in this equation is y. All the enthalpies we know already, so we can solve this for y. Therefore, I'll just keep going downwards. Therefore, y is just going to be H3 minus H2 over H6 minus H2. Okay, it's exactly the same process that we do, the interpolation process that we do when we're doing finding the quality, right? So we have all these values. We can solve for this, and this ends up being 14.62%. Okay, so what is that telling us? 14% or 15%, let's approximate it, 15% of the mass of water that's flowing through the system goes into our open feed water heater. And the 85% goes into the second turbine, right? So let's have a look at the system again, this guy here. When we get to the split, the one in green here, we get to the split here, yeah, about 15%, approximately 15% goes this way, and the other 85% goes this way. Okay, so only 85% of that mass flow rate is going to go through the second turbine, turbine 2, and only 85% is going to go through the condenser. So if you want to evaluate what is the heat rejection that happens here on this guy here, we need to take into account that only 85% of that mass is going into there. So now we can be happy and solve part A. There you go, there it is. Okay. Probably should have done this further down. Okay, so we can finish this off. My work net will be, what I have here, Q in is going to be 2692.2. And this other guy here, minus 1675.7. They already take into account pi. So this guy here is just found 0.1462. So the work net of this Rankine cycle with regeneration is 1016.5 liters per kilogram. Okay, so this is the difference in what goes in Q in and out, and it turns out to be 1,000 kilojoules per kilogram. The next part of the problem is asking us what is the thermal efficiency of this fellow. Well, after all this hard work, that's probably the easiest part for you guys, right? That's the feel-good part of the problem. As we know, thermal efficiency is work net over the Q in, or related to Q in to Q out. So this is simply going to be 1016.5 divided by the 92.2. This is about 37.8%, approximately.